All right, now we're recording. And let's see, where did we finish up last time? We were doing functions, right? Functions. User-defined functions. That was chapter 6, right? Function files, okay. Now we're going to be doing chapter 7, which is user-controlled input and output. This is essentially where you program in a option for the whoever's using the program to enter something in to into your function or into the program that will be used by the program or spit out by the program or something or other. And this can get quite complex. You can actually have the user input things in that will actually alter the program, that will change what the program does. That can be the case. And that's really where we're trying to get to in programming. We're trying to get to a point where we write a program that somebody uses to do some particular function, but they provide some of the information so that they can customize it or make sure that it's doing exactly what they want it to do, right? So chapter 7, this is on, I don't know what page this is, 244. We'll start with some very simple stuff. First one is the input function. We're going to go ahead and use similar syntax that we've used before here. I'm going to clear some stuff up here and throw away some of my functions up here in other files. Okay. We're going to start off using very similar syntax as before, where we're going to assign a variable to something. We're going to say z is equal to input. So in other words, we're telling MATLAB to put something into this variable that we're going to call z. And we're going to say enter a value in single quotes here. And you remember that whenever you want MATLAB to think that something is a word, you have to put it into single quotes. And then we go ahead and press enter. And MATLAB asks, or MATLAB puts enter a value out on the screen. It has the blinking cursor here, which means it's waiting for us to do something. So we enter in a value, 45, and hit enter. And it says z equals 45 and stores it over here in your workspace. Hopefully you can see that that might be very useful. And immediately you should start thinking of things that you've already written, programs you've already written, functions you've already written, where you could actually integrate that into the program. Where you ask the user to enter a value, they enter a value, and then now that's a stored value and you can use it in your program. Also, you can, in this particular case, if I do this again, enter a value, I can enter in a matrix value because MATLAB treats a matrix just like it treats a number, pretty much. So I can do 4, 7, 8, 12, negative 89 or whatever else, enter that in and it does the same thing. It does that just fine. If you could also be a little more specific, if you wanted to tell the user to enter a value in square brackets or something, then you could do that as well so that they know that you're looking for something that is defined as an array or a matrix. You could do it that way and it just asks a different question. No big deal. It can understand either one. If you want this input to be in if you want this input to be text, you should probably tell the user how to enter it if you're going to use the input function. So for example, if we want them to enter their name, then we say, we put it in single quotes, right? So enter your name or a name or whatever. in single quotes, and then I can put in my name, Jared, right? But if I don't put it in single quotes, it doesn't know what to do with it because it's letters. So I put it in single quotes, then it knows what to do with it. Now let's put it into this array over here. This variable is now a text, or what we call a, we usually, what do they call that? I just blanked on it. They call it a string. So if you have something entered in as text into a program, into a computing language, they usually call that a string, or a string of letters. So that's a string.
So is there a way to do it where you don't have to hit Z equals input every time, where you just hit Z and it'll pop it up?
Yeah, if I go ahead and hit Z right now in my window here, if I hit Z right now, it brings up Jared. Is that what you mean?
Well, I'm just thinking ahead for my final project, and I want it, if I want the rise and run of something, if you start a program, you have to enter the rise, so you just have to
Yeah, so in your
type input rise.
so in your function, you would only have to put in this command one time for each thing that you want entered in. But this is a function command, so you do have to put that in your code. You can't substitute. You can't define a variable as a function. I think that's what you're saying. So you couldn't just say Z is this. You could make a function file that you could name Z if you wanted to. That does this. So if you wanted to make your own function that was called Z, and inside that function it says input whatever it is. I mean, all you'd really be doing is replacing input with Z. So it'd be a few less letters to type in, but it wouldn't really do anything for you. So this is an actual function. So when you assign it to a variable, it just puts whatever the output of this function. The input function has an output, which is whatever you put in here, and then whatever is entered rather in here. And if we actually go in and put in here, so if we go and look at the help for input, it will tell us all the different things we can do with it. So the input expects a prompt that you're going to put in when you're programming input, and then whatever the user puts on the screen, it plugs into whatever you assign to the result. If you just put in input and don't assign it to any particular variable, of course it will just assign it to the generic variable answer, ANS. So if I just do that, then it'll still let me put in some kind of input, the name, right? Whatever my name is, but it will just assign it to the generic answer variable. So if I want to do something else, like here they do some examples here. We have example 7.1. We're going to try to calculate the position of an object in free fall. We're dropping something out of the Leaning Tower of Pizza, right? And the formula is distance. The distance that it's fallen is 1/2 times the gravitational constant, 9.8 meters squared, times the time squared. So, and actually, I guess they want us to do it on the moon, not on the Earth. On the moon, it's not 9.8; it's 1/6 of that, which is 1.6. And so we're gonna make a little free fall problem here. And you know, they like to annotate things. Free fall example, whatever. And then we're going to go ahead and request input from the user. So you could do that, request input, user input. And the input that we're going to request is that G, or actually this is going to be used for any planet. G equals input what is the acceleration due to gravity on the rock that you live on? Right? Put that in single quotes. So that's going to be our input. And then the user will, of course, go ahead and put in whatever their acceleration is, 1.6 or something like that in meters per second. Maybe we should say in meters per second squared or whatever. And then we could actually say start. They want to do a starting point. So starting point is going to equal the input from the question. Starting time. So what is your start time? Right. So they're going to have an input just about everything in this, and that's fine too. Go ahead and put in what is our start time. We'll say 10. And then, and you could put this in a function. We could write this into a function as well, so that it just runs this function, and then uses these things to calculate the result. That's a little bit. There's a little bit of a challenge with that because remember that when you create a function, it tends to use variables that are inside the function, but you're going to be using variables out here, so we have to make sure that that's possible. Actually, let's just go ahead and do that. Let's just save us some time and do it that way. So let's start a script here and let's do some user input. Let's go ahead and copy this, put it up here, paste it up here. We'll copy this one, put it up here. Go ahead and copy these two lines just for kicks and giggles. Copy. Actually, you know what I'm going to do? I'm going to copy this whole thing because I forgot that we can open a new function, right? I always forget that for some reason. I'll paste this in here. So our function output argument is going to be distance traveled, something like that. And we'll call this free fall. And the input arguments I'm going to leave blank. I'm just going to leave that as a null set of input arguments. And we're going to ask for all of our input here. G input, start input, finish input. They want finish to be an input as well. Input. What is your finish time? Right. Question mark, so on and so forth. So asking these things, and what these things should do is they should create some variables, right? But are they going to create variables out here in the workspace or within our function? What does the input function do? We're going to find that out in just a second when we run this thing. And then we'll do an increment, time increment, which will equal what input, what time increments would you like calculated. So apparently we're going to calculate more than one time. That's fine. So you can put an array of numbers in there if they want. And then we're going to actually calculate the time. So we're going to calculate the time. It's going to equal an array of numbers that's going to be start, and then semicolon increment, and then semicolon finish. Right? And we'll express that. And then we'll go ahead and calculate the distance as well. Distance. Now we're using capital D distance because that's our actual output. And we want to maybe output that to the screen, maybe not, I don't know. Maybe we'll do something different. Our distance will be 1/2, our formula, right? 1/2. And remember, we're going to have some possible, um, we might get, let's see, we have to allow for the fact that they might enter in some arrays of numbers. So we'll do a dot times 1/2 dot times g, and do a dot times t, and then squared, just in case they decide to make this run parallel on many different sets of numbers. And let's go ahead and see how that works. Let's give it a go. Let's run this. It's going to save it for us. Free fall, replacing another one apparently. And what's the acceleration due to the rock we live on? Let's do 9.8. We'll be on Earth today. We'll know what's our start time. Start time will be 12. Our end time will be 54. Notice that it hasn't stored these variables over here. G is still 1.6 instead of 9.8. Start is not stored over here as 12. It's stored as 10 over here. So obviously we're not storing these in the workspace. So now we know that, and we want to know time increments of 1 second. Oops. I made a mistake. I used t instead of time here. I'll fix that. Let's do it again. 9.8 meters per second squared. Start at 10 seconds. End at 54 seconds. 1 second intervals. Oh, what did we do that? Oh, we have to do dot squared. I didn't do that. There's always some mistake. Okay, now we do it again. Let's see if we can make it through the program. 9.8, I should use something simple. 10, 54, 1. There we go. Now we've got an array of numbers that it's calculated the fall distance for between 10 and 54. So those are all the distances, and the distances are times 10 to the 4th. So after 10 seconds of falling, you're falling really fast. After 10 seconds of falling, in the next second you go from 490 feet to 590. No, that's not right. 4,900 feet. There we go. To 5,930. So it's fall 1,000 feet in a second. In 1 second after 10 seconds of free fall. So it really gets moving. And then you're up here into the 10,000s of feet and so on and so forth. Oh no, this would be hundreds, thousands, tens of thousands. So it's actually 490 to 593. So it's 100 feet in 1 second. 100 feet a second. That's still pretty fast. But when you get down here, you're going from 6,700 to 7,300 feet in a second. When you get down to here to your 50th second, so about a minute of free fall, you're going from 13,200 to 13,700, 500 feet a second. Really moving. Okay, so in the MATLAB example, though, they actually do some more. They actually plot this thing, so let's go ahead and plot it. And let's maybe let's not output anything. Let's just have an open output as well here, and we'll output a graph maybe of things, because that's what looks like they're doing here. They're doing a plot. So they're going to first do a log plot, but I'm going to first just do a regular plot. I'm just going to plot the results here. So I'm going to plot distance versus time. Time and distance. Time first and then distance. And then I'm going to do a log plot of time and distance. So log, and just do the same thing here. And then we're going to give it some labels. We'll title it. Give it a title, whatever you want to title it. D versus L. D versus T. Whatever you want to call it. And then you could label some axes as well. Since I'm doing two plots here, I might want to either use the hold function If you don't remember what the hold function does, of course you can come down here and do help. Hold. Hold sets the next plot property of the current figure and axes to add, so that you keeps essentially what it's going to do is it's going to hold the current plot and won't change anything. Let's see. So I think it should work if I do plot and then I do hold on like that. I think that should work for us. Let's try it out. Sometimes it's the best way to figure things out here. So let's do something a little simpler here. 10, 10, 100, 10. So there's our distance versus time. And let's see. Looks like it didn't do our log plot for us. So now we gotta figure out how we're gonna do that. So we could do this. We could do this another way, because what that did is essentially didn't allow the log plot to plot for us. So what we need to do is maybe split this into some subplots. So subplot see if I can remember how to do this. We want a 2 by 1. See 2. Let's 2 by 1 will work. 2, 1, 1, 2, 1, 2 will work too. And in the first spot will be this one, and then we'll do another subplot for the next one. But this one will be in the second plot space. Then we'll run it. 10, 10, 100, 1. There we go. So there's our plot with. And it gave us this for the second one, but not the first one. But anyway, so here's the one where we just plotted the time versus the distance, and this is what we would expect as as the time goes on. As we go from 10 seconds to 100 seconds, we expect to go further and further distance, longer and longer distance. But in a log plot, we would expect that line to be straight because this is an exponential curve. And the logarithm of an exponential is a line with a constant thing there. I don't really like the way it looks though, because I want it to look like it's falling. So I'm going to change my equation here to negative 1/2 g t times time squared, and I'm going to run it that one time. And now I'm going to do 10 meters per second, and I'm going to do the start time of 0 and the end time of 100. In increments of 1, and now it looks like it's falling, right? And you could actually do multiple times. So let's say that we want to, let's do this again. Let's run it. What's the acceleration due to gravity of the planet you live on? I want to do an array of times. Let's do an array of things. Let's do the moon, 1.6. Let's do the moon, or I did the moon. Let's do Mars, which is like 3. And let's do Earth, which is 10. And let's do, what's the worst one in the solar system? Probably Jupiter. I'm not sure though. Highest gravity in the solar system. Yeah. Let's see. The gravity, since Jupiter doesn't really have a surface, it's hard to determine this, but gravity on Mercury is pretty small. Surface gravity 3.7, which is about Mars's. Gravity on Venus, here we go. So it's a little bit less. Gravity on the moon, gravity on Mars, about Earth's. Gravity on Jupiter. equivalent to, oh, so it actually has much less gravity. No, it's actually more. Jupiter's surface gravity, 24.79 meters per second squared. Saturn's is about the same. Uranus is a little bit less. So 2.5. We'll call it 2.5. Let's do 2.5. No, 25 rather. So 25 meters per second squared. So that's our array of G's. Our start time will be 0. We'll go from we'll go from 0 again, and then we'll go to 10 again. And time increment's still 1. Okay, so this is a problem because our time is an array and our gravity is an array, but they're different arrays. And so what we need to do here is, let's try that. Let's see here. There is a way to do this, but I think we might have to use MeshGrid to do it. I'm pretty sure we have to use MeshGrid to do it. 0, and if we do, I'm not going to mess with it at the moment. But yeah, we'd have to do it. So if we're going to do this, we're going to have to do a MeshGrid between our time and our gravity. Well, maybe we can go ahead and try it. Let's go ahead and try it. So time, start to finish, we'll do a MeshGrid. So we'll use, so we're using G in time, so we'll use big G. And big time, and we'll let that equal a MeshGrid of little g and little time. And if you remember what MeshGrid does, it creates arrays that are now going to be they're going to have the same number of rows and same number of rows and columns so that we can multiply them together. And then we're going to change this in here to big G and big T, and hopefully I did this correctly. And we'll do our dot time stuff in here so that we can hopefully get this right. So we've got a MeshGrid of G and time, big G and big time. Distance now equals big G times big time. And then we go ahead and put big time by distance and big time by distance, and let's see if that works. Who knows? Go ahead and paste this back in here. And my start time is 0, end time is 10, 1. There we go. That's what we wanted to do. So now you can see the different accelerations on different planets. You've got this biggest one here, which would be Saturn, and then Earth. See the comparison there. So that's kind of cool. But now we know that if you ask questions, if you ask for input inside of a function, it doesn't store those things out here. Those things, those are stay as local variables still. If you put them in the command window, they go out here to the workspace, so they can be used anywhere. All right, there we go. Excuse me. So input, one of the simplest ways to get the user to put things into your program. Now, moving on to section 7.2, output options. There's quite a few more output options than there are input options. Well, that's not necessarily true, but we're going to teach you more. Okay. Let's see. So, of course, we know some output options already. If I just type the letter G, because G is stored in my workspace, it will print to the screen. The same is true in a function like this. If you want to take a variable that is inside of this function and you want to jump it out here to the workspace, you can actually do that. You can pick little g here, for example, and just type it in here and then run this. And if I run this, it'll ask me my questions. It'll step through the program like normal. Acceleration due to gravity, I want this to be this again. And I'm going to go with start time 0, finish time 100, time increments 10. And it does this, but but notice that it printed G out to the screen as well. It didn't change G over in the workspace, so I was wrong about that. But it does print it to the screen because that's part of the program. So here's G. Right? It also printed big G and big time because I forgot to suppress that output. So you have a couple of different ways to put output on. You can just type a number in, or you can put something in. You can define a variable without the semicolon, because the semicolon, of course, suppresses the output. We already know those kinds of output, but they can be very useful and very helpful in many different ways. But there are other ways that we can do it as well. There is, of course, going to be an output function, which we're going to call the display function. So it's the display function. So if I put display G, for example. Sorry, did somebody say something? No? Okay. Then it will actually just give that number. It's not going to print it as G equals something. It just puts the number on the screen. So that can be quite nice. You can do that within a function as well. So if I come up here and I put in disp, and put G in there, and then I run this function, and it asks its questions, and I answer my questions, and so on and so forth. It should display G somewhere. Where did it go? Oh, it's right here. It just displays it, but it doesn't say G equals, so it's this array right here. So that's just one thing that display can do. Another thing that display can do, though, is it can actually display things with text. So if I use, and if you're following along, we're on 248, I guess. Excuse me. Oops. So you can display text like, here is the display, or whatever. And if you do that, it will just display that text on the screen. You've got to put it in the single quotes, and that's fine. But you can use that in conjunction with multiple display commands. So we can do that display command, and then we can follow it with another display command to display G. Right? And we could change this to maybe display, here is the gravity, right? Oops, won't let me do both of them at once. I'm going to put it here. Command window doesn't give you all that option, all the many options to do it, but here is the gravity. Okay, so we go ahead and put that in there and we run it, and we go ahead and do everything that we're doing. And it says, here is the gravity, and then it displays this thing next, right? So, of course, that can be quite useful for telling your user different things. Confirming to your user, if your user types in G, for example, then you can say, this is what you typed. Did you mean to type that? You could do stuff like, my favorite. Are you sure you meant to quit, my beautiful right? So you can put this in there, and that can be one line, and if they hit quit again, then you can display, are you really sure? And you can display it again, right? And then you can just really annoy people to death with unending messages that you send to them when they hit quit. There are many programs that have that joke in them, but anyway. So the display function can be quite useful. It does have its limitations. Let's see what else it can do just really quick from help. Remember that help is very useful for trying to learn how to use these things. Oh man, you got all kinds of things going on here. Lots of information. Start right here. So display is called for the object X. Semicolon is not used to terminate a statement. So here we have display. So this is creating they're creating an inline text and then displaying this here. And then they can actually do it. There's all kinds of things you can do with this. It's obviously going beyond what we've taught just now, but we'll learn some more. Okay. At the bottom of page 249 and going into page 250, they create a conversation where they just write a bunch of displays and inputs and actually not even inputs, just displays. They just create a bunch of displays and then they create this simulated conversation, which was kind of boring. Later on, we'll learn how to actually make a simulated conversation where your program can respond to the question that is answered. So how the user answers the question can actually determine what is the next thing that the computer will spit out to the screen. We'll learn how to do that later. It's much more interesting that way. Okay, now a new kind of output function, a couple of new kinds of output functions, which are called formatted outputs. So they use this, they call this fprintf, which is formatted print to the screen function or something like that. I don't know. But the fprintf function, excuse me, it allows you to choose what kind of format you're going to have your output be. If you're not sure what that means, remember that computers really are only dealing with numbers. Everything that they see is a number. Hold on just one second. So a word to a computer is just a specific set of numbers that is where each number is connected to a character, like A has a particular number associated with it, B has a particular number associated with it. Excuse me. So a computer looks at everything as just these binary numbers. So you have to tell the computer if something is supposed to be treated like a word. You know, if you don't tell the computer to treat it like a word, it might do some math with your word and then it screws up your word, right? And so we want to be able to, in many situations, tell MATLAB that this particular thing is going to be treated like a word and not like a variable name or numbers or something else. And so this is what this particular function is used for, the fprintf. So let's do an example of this that hopefully will clear this up a little bit for you, because I know that that's not entirely clear. It's about as clear as mud. But let's go ahead and define a variable cows to equal 5, just like in the book. We'll suppress that output. And then we'll do an fprintf here. Remember that cows is equal to a number. We've defined it as a number. It's not a name. It's not a word. It's a number. It's 5. So we want to use the fprintf function now to print something that's to the screen. And this is what we want to print to the screen. There are, now we want to say a number here. So I'm just going to leave an underscore for space. There are a certain number of there are 5 cows in the pasture right now. Okay, so this is something that we can sink our teeth into quite literally in Nebraska. Cows in the pasture means beef on the plate, right? Now, fprintf is going to look at this and it's going to say, okay, I want to print this string because this is a sentence of words. We told it's a string. We said MATLAB, this is a string because it's got these quotes on either side of it. But it also wants to plug something into this string of things. It wants to include something in here that we've already defined, and one of those things that we could plug in is cows. We could also plug in start or G or any of the other things we have up here. But we're going to use cows because we defined it specifically for this problem. So over here we want to put in cows. We want to tell it what the name of our variable is we're going to plug in, cows. And then right here we're going to tell it where to put it in by using this syntax, %f, just like that. %d. They use %d. So you can actually do, there's several different ones you can do. You can do %e for exponential format. You can do %g for fixed point or exponential, whichever is shorter. And you can do %c for characters. For character information, so you would actually put in a letter, or you can do %s to put in a string, so like a bunch of words, or %d for decimal format. There is actually a %f as well, which is %f is a fixed point notation. So we could have put in fixed point notation as well. If we put in %, so this essentially is the thing that's going to tell us the format we want the thing to be put in as. So let's try this and see what works, see what happens. So it prints out this thing that says there are 5 cows in the pasture, and then it puts in the prompt. Now let's do the next one. Let's do another one. Instead of %d, let's try %f and see what the change is. If you put in %f, it gives you what's called the fixed point notation, which is going to give you many, many decimal points out to as many as you've told it to give. And you can actually tell it how many to give. You can say, I think you can put %f2 or %f3. I think that's how it works. Let's try it really quick. So if I put %f2 here, oh, that's not right. I did it the wrong way. %2f maybe? I can't remember how it goes. Let's see, oh, there it is. It goes %. So there's actually 2 numbers you put in. You put %8. So if I do 2.2, for example, no, it has to be 8 has to be the number of. So 8.2. There we go. So the 8 is the number of total digits that you will include in the number, but only 2 of them can be past the decimal point. So we could have as many as 8 numbers to the left here, but only 2 past the decimal point, and you can see it left a huge space for all those 8 numbers here. So maybe we don't want to have that huge space, so we do go to 2.2 or 1.2 or even 0.2, but we don't want to have 0 because we want to have at least, if we put 2.2, we're going to have a total of 2 digits, and you can have as many as 2 past the decimal point. So it gives us that. And if we do 1.2, let's see what that gives us. 1.2. Then it starts to look a little bit more clean. But anyway, these different formats are different ways. If we use the E format instead of the F format, the exponential format, let's see what that gives us. So it's 5 times something to the that. We could also force different sizes in the E format, so we can have 1.2 in the E format, and it shortens it down for you. So you can do all kinds of things to format specifically what you want to come out in this fprintf function. And they give you a bunch of the different types here on page 251, the %f, the %e, the %d, %g, %c, and %s. The %s is another one, is one that we kind of want to, well, I guess the n is the next one they show, but they don't even show that with the, no, %f is the next one. No, I guess they don't actually show you the S one, but S allows you to put a string in there. So let's show you that one really quick. So we're going to define now a new thing. We'll define a new function as we'll call it a word, for example, and we'll put in a word. Word is going to equal Jared. Why not? There. So that's my variable that I've just applied. And you can see over here that since I put it in quotes, it defines it as a string in my workspace. A string is defined by a little ABC box over here. So that is a string. And then if I want to say, if I want to put something in here, I can use my %string now format. And instead of putting in cows, I can put in my word, right? You know, say there are Jared cows in the pasture, whatever. So this allows you to put things out, to print things out to the screen in many different formats and many different ways that can be very controllable. All right. Another thing that you should know when you're working with strings, you can force these strings to move to the next line. So it's what it's called a carriage return. It's a /n. Is it forward slash or backslash? Backslash n. So you go /n. That takes you to a carriage return. So there are Jared return and cow, or there are Jared cows return in the pasture, right? And because I put a space after that n, it gave me a little indent here. If I put the space, if I put no space after the n, then it won't do it. And it doesn't matter if that's right next to the in. If you have /n, it knows what to do, and then the very next letter is going to be a new word. So you can do it many different ways. There's also some commands for doing an indent, for doing a tab. I think the tab is actually just /t, if I remember correctly. So if we do a /t, gives you a tab. So there's your tab. So you can do formatting when you're dealing with, when you're working with strings. Now, and they have them on the next page, 252. So there's the line feed, which, actually the line feed is different than carriage return. But it's a different command, but it's pretty much the same thing. The tab is /t, and then the /b is a backspace. So there you go, some string format commands. Let's see, what else? What else? You can use fprintf with arrays as well. It will print an array out as well as it'll print anything else out, so nothing really new there. Here's a nice little tool. Before, when we were making tables, we often would have two variables, like this is the bottom of page 252. Two tables of numbers, feed equals 1 to 3, right? Oops. Feet equals 1 to 3. And inches You know, like a little conversion table here, where inches is equal to feet dot times 12. And then we go ahead and build a new array. We call it conversions. We build this array and it is equal to, so they do feet and then inches, right? So 1 foot is 12 inches, 2 feet is 24 inches, 3 feet is 36 inches, and so on and so forth. And we could also invert that array to make a table like that, and that works too. But you can also use the fprintf function to do this. And this one gives you the option of formatting your table a little bit more succinctly. And you could, so in this example, they're going to put this, and it's still going to print it off as a string. It's printing it off as text to the screen, essentially. So you put it in quotes still, and we're going to use the percent, or we're going to use the %f thing, and we're going to do 4 total digits with 2 beyond the decimal place for the first one. And then the second one, we're going to do 7 so that it gives it a little bit of space. So we're doing 7 total digits with 2 beyond the decimal place. And they're both going to be the floating point numbers. We go ahead and close that up, and we're going to, and we're going to do a carriage return as well in there. So we'll throw on a /n and put a space there if we want. And then we'll do this with using our table conversions. And this is what it prints. That's not what I wanted it to print, but that is what it printed. So I want to switch back to conversions being what it used to be, like that, and then do this. Now it's done what I wanted to do, right? So one foot is 12 inches, 2 feet is 24 inches. That's not what I wanted to do. I wanted to do this. fprintf, there we go. So then when I did fprintf, it actually will print the first one and then the second one. And then,
If you change that to 4.0 instead of 4.2, it'll be just 1, 2, and 3.
Yeah.
Instead of
Yeah, if you don't want any decimal points, I'm just trying to do it how they do it in the book. So if you don't want any decimal points, you can take off the 4 point. You can take off the point thing here, and that will allow you 4 points. In fact, for these, you could do 1.0 for the first one because you only have 1 digit out here, and for these second ones, you could do 2.0 because you only have 2. But then they would be right next to each other. Let's see what that looks like. So if we just did, if we just do 1.0, because they only have 1 number in each of those, first column, and then you do 2.0 here, the formatting will be different. They'll be right next to each other though, so maybe if you want to spread them out, you flip this off, and you don't have any decimal points. But if you need decimal points, if your numbers actually do have some resolution out there in the tenths or hundredths, then you can adjust it accordingly. And the point is that you can choose it that way, right? So anyway, the fprintf just has this functionality of being able to do all kinds of things the way that you want to do them, so that you can choose that. And programmers really like to choose that often now. And the other thing is that you can actually have the user choose those things sometimes, or you can have the program choose it. So those things can be done automatically as well, depending on how you program it. We'll learn more about that later. Okay, so more output functions include things like, well, more input functions, I guess. No, that's not right. This is still output. So we're still doing output. In this case, you can use the fprint function. Instead of printing it to the screen, you can actually print something to a file. So you can print something to the workspace, for example, or not the workspace, but the current folder. So you can open up a file out here and print something to the file. It's like saving data, right? And the way that you do this, first of all, you have to have a file out here. So you can either go out here and create a file for opening these, or you can actually just create it right within MATLAB. So to do this, you need to name the file something, file Jared or something, whatever you want to call it. And then file Jared is going to equal now, and that has to obey MATLAB's rules for file naming. So it has to start with a letter, right? Can't start with a number. Can't have any funky things like slashes or colons in it or anything like that. It can have underscores in it though. And then we're going to use a command we call fopen, which opens a new file and saves it as whatever your file name is. Mine is file Jared. And then, oh no it doesn't, sorry. The file ID is, I think, going to save something in the workspace. And this is where you name the file that goes out into the current folder. So I name it inside of the function fopen, and I'll just call it output file. Output file. And then you actually have to tell it what kind of file to be. It can be a .text or a .mat or a .whatever. So you're going to give it its form, the type of file it's going to be when you spit it out there. And then you put a we have to put a type of file, what we're going to be doing to it, I guess. Let's see. Yeah. So this next thing, we're going to choose what we want to do with this file. In this particular thing, we want to write to it. And I believe you can also open a file for reading from as well. And there's maybe even some other ones, but this one we're going to write to it, so it's WT in quotes again. And that tells MATLAB that we're opening this file called output file.txt, and we're going to write to it. Okay, congratulations, we've just done it. So there's our little file Jared right there. Right? Let's put a value of 3 in it. I don't know why. But then we should have a file over here as well. I'm not seeing it though. Well, there it is, output file.txt. So it did show up there in the current folder. We created that new file, output file.txt. And as we now print things to that file, we can use fprint to print to that file. That's where that information will go. So fprintf. And we're going to choose our file ID, which is, our file ID is file Jared. That's the one that MATLAB, that's the nickname that MATLAB has for it, so that's the name we use here. And we're going to go ahead and, let's see, that, yeah, the file ID, we can just put it just like that because it's a variable for MATLAB. I believe that you can also use the file name. I think you can also put output file.txt in quotes here, but we'll figure that out in just a second. We'll try it both ways. And then we're going to go ahead and put in whatever we're going to put into that. I'm just going to put in a number like 678 into it for now and see what we get. Nope, doesn't like that. It wants the format to be, let's see, so it still wants to actually, yeah, it still wants us to type in like we had before. So fprintf into file Jared, and we're going to still put into quotes the things, into single quotes, the thing that we're going to put in here. So input is whatever it is. Put our %d here, close those quotes, and then we'll put in our number. We'll put in 100 or whatever. It returns an answer, and the answer is not the thing that we put in. This is the thing that we put in. Input is 100. And if we go over here to our output file.txt and open it up, it'll allow us to open up this text file here, hopefully. And that's what's in that file. Input is 100. So it's actually stored that information in the file. But it's given the answer 12 here because 12 is the number, of characters that it's put in there, or the number, I believe it's the number of characters. It's the number of bytes. So each byte is a character in the word, and then the number is actually, each character is a byte, takes a byte, and each number, I think that each number is also a byte. It might be 2 bytes for a number though. So let's count. 1, 2, 3, 4, 5, 6 for the space, 7, 8, 9, 10, 11, 12. So each number is a single byte. So we're good. So that's the number of characters in essence. All right. There's a couple of hints on page 254. Since you're using the % sign inside of this fprintf thing, if you need to use a % sign, you actually have to use a double % sign. So if you need this print off, the input is not D, but 100%. Then you would put a double % sign in a row after this, and then it would print that to the output file. The input is 100%, and then it just prints one after the other here. It doesn't replace the original text. But this is a very useful thing because if you're writing data, if you need to write data to a file, then you can just have this go in one after another, and then it can read that data and that whatever that information is, you can store that information one after the other. And if you need spaces or tabs in between each of these pieces of data, then you would go ahead and put those in. It's most often you want to put a tab in for data because computer programs like Excel recognize the tab as the next column kind of thing. So it's a good idea to put in a tab. That way, when you open up this file, you've got an actual. It's gone to the next tab here, which doesn't look any different. Oh no, right here is the tab right here. So the next time I do it, since I have a tab at the end of that, every single one that I put in after that will have a space in between it, that tab space. Okay, so example 7.2, they do the free fall, but they do formatted output, so it's pretty much the same as we did before, except instead of using just display, you're going to use fprintf as well to print stuff to the screen. I'm not going to go through it. It's not that hard, not that different than we've done. There's another fprintf called sprintf, and it does a different thing. Instead of sending out, instead of just sending the stuff that's inside of the fprintf command, it also gives that stuff a name. It gives the whatever this formatted string is that you're sending out, it gives it an actual name. And let's see here. We're showing a good example of this, but I'm not sure I want to go through that whole thing just to show you how this is used. So if you go down page 257, you'll notice where this sprintf is used. Somewhere, where is it used? Right here. It's used about, if you look at the second from the bottom comment line, so there's a comment line that says plot the results, and if you look 2 lines above that on page 257, you see the line text equals input equals sprint. So let's look at this. First of all, let's look at this one right here and open up Word. This is the thing that no, that's not the one. Sorry. When I created my file, Jared, if I open this up, it doesn't show what's in the output file, what I printed to that file. It just doesn't show there. But if I use the sprintf one, it does. The sprintf one assigns this text box a variable name. So let's do this. Let's just do this really quick. Text in equals sprintf max was whatever it was. F they're using here. And then we close that quote and we put in maximum. So this one is going to take that, whatever that variable is, maximum, plug it in here just like before. So if we define maximum to equal 10 or whatever, and then we run our sprintf, right? It says the max was 10, so that's very much like the fprintf, except maximum, let's see, the word I say I didn't use maximum. What did I use? Text in. Okay, so this text in now is a saved thing. So now it's saved it as this. It's kind of like saving a text box. You've saved this thing that says the max in is whatever it is, but it doesn't necessarily plug in the number right now. It can plug it in later as well. So if I get that max from something, if I look for the maximum in an array or something, look for the maximum on a chart, and then plug that number in, it will actually use that number, and then you can put that in to your text for your title, for example. You can use that as a title, or you can use it in a text box, or you can use it on your X label or your Y label. Whatever, you can start to use text, you can start to use numerical input from wherever into text, and then use that text wherever you want in the function. So that's quite useful. Okay, other forms of output. We have some forms of table output, for example. So this one's a nice one. We should have taught you a long time ago, but it didn't make sense to teach it to you a long time ago because we were trying to teach you other things. So if you have, in this case, they're going to give us, we want G equal this array 9.8 and 1.6, right? Got my square bracket backwards there. 9.8, 1.6.
Yeah.
And we want oops. Ah. Okay, fine. Let's try that again. G is equal to 9.8, 1.6, and then D is going to equal 0.5 times G times 100 squared. So we've got our G, we've got our D, and then we've got another thing that we're going to call P, and it's going to be defined as two strings. And we can make arrays of strings using these curly looking brackets. You can make an array of strings doing this. This is often called, I can't remember what they call this, but anyway, it's an array of words essentially. So we're going to put an array of words together, earth, and put them in quotes again, single quotes, and then single quotes and moon. So there's our array of words, looks like that. And then we can actually go ahead and make a table. So you're going to love this. B, G, and D, right? Oops. My shift key is not working for me. So this gives us that's not what I wanted to do. Sure it is, I guess. Yeah, so P is the planet, G is the gravitational constant, D is the distance that it falls in 100 seconds. Might do a better one if we did. I think that P. I don't think you actually have to put these in quotes when they're inside of these curly brackets. So we could get rid of the Earth, get rid of it that way. Define it. No, I guess it can't. Oh well. But anyway, can do it this way. So that's kind of a nice way to make a table. Oh, and the next one they tell us how we can change the names of the categories. So that's kind of nice. So if we want to do, if we do this display, we do table rather, P, G, and D, and then we can actually put a comma, and then we can do variable names in capital, V and A, V and N, rather, names. Variable names, and then we make an array of variable names, string array. So variable names are planet, gravity, and distance. So now we do that, and it allows us to make a little nicer display. And there's other things you can do with display, or rather with the table. And you can also use the display with that, so that it doesn't come out with this answer. If you just want to, whenever you don't want that answer thing to come out, answer equals thing, you generally want to use the display function. So we use our table function just like before, but then we just do the display of that table. Display this stuff. Going to put another parenthesis all around the outside of it, and then it just displays it without an answer equals thing, right? So quite useful. Okay, finally, we got through all those different outputs. So let's go on to section 7.3, graphical input. And then we'll start looking at how we can clean up our scripts a little bit. Let's take a little bit of a break. I'm going to get a drink. Come back in 5 minutes or so.
Like, get it while you can. You broke the TV? How's you doing next door? What? How's you doing next door? What? I don't know what place this is. Oh, settle down, guys. I don't care. It's like, what's wrong? That's just what I always say. It's just, it's not even new. Oh, yeah, Andy uses the controls. You playing? Oh my god. That's what the three of us are. Are you guys playing right now? Yes. Yes, you are. Are you guys playing like squad? Yeah, second last week. I did all of it. I'm pretty sure I helped. I got 4 kills and 0. So they basically all think that technically that tells right there. Why did you jump so soon? Alright, look for the marker if we go this way. He's not. He's just going wherever he wants. Yeah, cool. Am I shooting the last one? Mm-hmm. Where the markers are. Yeah, you guys are right up there. No, just on the ground. That's just the compass. So you go right down where you are. Straight for the path. I made it. What are you doing? I'm just saying. I'm not part of this game. I'll go get you. And come back. Something wrong. No, it doesn't. You're definitely. Hang on. Take a shit. Take it. With what? You a damn phone. Go pick up a new one. How's the it's easier to aim, but it's not regular. You have to stay. You have to stay. There's a way. It's not coming. Looking there. I'm still
Okay, we're back. Let's finish this up here. Graphical input. So, let's see here. We don't have a figure window open here. So when you have a figure window open, MATLAB knows every point that's on the figure or on the plot that you've plotted. And so it can you can actually use that as input. We use the G input command, and we can, if we do it right now, we can do it right now. We say G input, and let's see, 1. Okay, so we don't have a figure in our window. And so it's going to be a little confused. But what it's going to do is it's going to put a little cursor up here on your window and allow you to choose a point somewhere. And then it will use that as the input. So now it's stored in the thing answer, the point that I chose, even though there was nothing in the window. You could do it again and choose 3 points. So I come up here, and now that I actually have something on the graph, I can know that I'm choosing at about 0.2 and about 0.1 right there. 0.2, 0.1, and then it wants another one. So I'll go up to about 0.8, about 0.3. Usually it snaps onto it pretty easily. And then I'll come down here to 0, 0 and see if I can choose. I'll go down into the negatives. So it even lets me choose in the negative. And then it stores that into my workspace and we're good to go. You can also assign it to values. So if I wanted to do the first one and assign it to a single value, I could call it point, for example, equals G input 1. Right? And then it assigns whatever I click on to the variable point right there. And it's given it the coordinates for that point. And I can do 3 separate points even. So if I do this one, G input 3, I need to assign that to 3 separate points. So I need to assign it to an array of things. I'll call it A, comma, B, comma, C, for example. G input 3. This will be A, this will be B, this will be C. Each one of those will be wow, I picked something. I really picked 111 for C. That's pretty amazing. But anyway, it stores them into the actual variables then and stores them over here in the workspace as well. Where A gets all of your X components. No, sorry. Is that right? What did I just do? Oh, I think that if you ask, let's see, that's not right. No, that should be right. Oh, I know. That does 3 dimensions. If I set it equal to 3 variables here, it does it in 3 dimensions, but I was only in 2 dimensions. So it set all of my C values, all my Z values to 1, apparently, because I was only in a 2-dimensional graph. So if I'm going to do 3 numbers here, like I just did, I need to set it equal to 2 variables. Probably makes more sense to call them X and Y because that's what they're going to be, your X and your Y coordinates for those 3 points. So I can choose 3 points, and then I'll put the X and Y coordinates in there. And you can choose as many points as you want. You just have to tell it how many you want. And if you don't want to choose a certain number of points, then you can just put in G input like that, and it'll just it'll continue accepting points. You can just keep clicking as many as you want until you're done, and you hit enter. And then it'll just put in that however many points you clicked. So that's one way of getting input from the user. And you can, obviously, you can use this to input data from a graph or points from a graph. That's obvious. But it should be a little bit obvious that you can use this, that this is actually what is used with a mouse on a screen. This is actually how Windows works. This is very similar to the kind of programming that was done when Steve Jobs and Steve Wozniak and what's his name from Microsoft Word, Bill Gates, got together in Steve Wozniak's garage, parents' garage. It wasn't even his garage, I think it was his parents' garage. And they started programming what became Windows and the Macintosh operating system. They all worked on that together, and that's what they were doing. You'd move this mouse to a point on the screen, and when you clicked, the information for that particular coordinate would go into a program telling the computer what to do with that click. If it should open a window, if it should close a window, if it should save a file, whatever it is. Because at different positions on the window were these different quote-unquote buttons that were programmed into specific spaces on the window. And at the very beginning, it really was that simple. It was not, you couldn't necessarily move windows around very easily like you can now because those buttons were fixed. Nowadays, they've even written it in so that you can move those things around and it works out just fine. But this is the beginnings of graphical user interface. which is what Windows and Macintosh and what all of your cell phones use. They all use a graphical user interface where you're pointing to something on their screen, and the screen knows that when you touch that part of it or you click on that part of it, it knows what to do. G input. Okay, now we're going to move here on to some different things that are, they do have something, I mean, they still have to do with input and output kind of things, but it's not necessarily obvious that it is. So let's go ahead and go down here and clear everything out, and you'll see everything out, clear everything out. Okay, there we go. All right. Now, a while ago we explained to you that MATLAB has these tools for organizing your script files. So when you write a script file up here, you can organize it in different ways. And that came with using things like breakpoints. You can also use the, insert a section right here. So you can put in sections. You can indent, you can do different kinds of commenting. So lots of different things here. And the thing that we're going to talk about this time is the sections. So we're going to start off by creating a file, a script with some sections in it. And this one we're going to start off with some comment lines. Maybe start off with our name and the comment line, that double comment line up there, Jared Daly's. File, do not touch pain of death. Right? And then we put in another comment file to maybe explain what this is all about. You know, this might be my class notes file or something like that. Whatever it is. Another comment line. You can put in, you know, lots of comment lines, whatever you want to do. Now I'm going to start, and every time I start, I go ahead and I do a clear and a CLC, and that's fine. And actually, in this, you can actually do these clear CLC, and they do a close all as well. Do a close all. You can do those one after the other with the commas. I think you can do that in the command window, but I keep forgetting to put in the commas. And then you could explain what that does if you want to, or you could actually start a new section. So let's go ahead and insert a new section, and we'll start this next part. Puts in the little line there, tells me which section I'm in, starts off with a double comment line again, so I can tell me what I'm doing. I'm going to do problem 1, or whatever. Right? And then I go ahead, maybe there's a section A like they do in the book. But notice that the section I'm in is highlighted yellow, the section I'm not in is not highlighted at all. And then you just keep doing these things, and then you're organizing your work as you go. I like to, at the end of each section, to put a couple of lines in there to give myself a little white space so that it's really obvious where the next section is. Some people like to, some people don't. It's up to you. You're not hurting the computer to put space in there or anything. But then you can put in multiple sections. One of the advantages of doing this is if you want to print your work off or publish it, you can do that pretty easily doing this. And you can include things like plots. So let's go ahead and do a simple plot here really quick. Let's do the one they do in the book. They do this one in the book. Actually, we're on page 261 in case you're wondering. 0 by steps of 0.1 to 10. And then we're doing y equals exponential of x. And then we're going to call this figure 1. And we're going to plot it. X comma y. And we're going to give it a title. We'll call it my plot. And maybe even do some X labeling and some Y labeling. You could do that here too. You could do this like if you do a comma here and do an X label. X. Whatever. Turn on the grid if you want. Grid on. Okay, so that's pretty good. Then we go ahead and we run this thing. Maybe let's put in another of these things. We'll give ourselves a little pause here maybe. Give ourselves a couple of spaces. And then we'll insert another section, whatever. And then we'll go ahead and run this. We'll call it example. And we'll save it. We'll run it. So there's my plot. That's great. Let's see, what else do I have to do? I think we're good. So now if I go up here and I use my publish feature, now bear in mind this is the first time I've done this. So let's make sure I can do this. I'm just going to try to publish it just like this. Publish example. I think what it's going to do it didn't do it. Publish. Let's edit the publishing options. It's going to output format in HTML. I don't want us to do it in PDF. So I can see it. It's going to output it. Oh, so it did output it. Okay. So now I'm going to publish it again. Publish example. And it should come up as a PDF over here. Oh no, because it's going to come up in, yeah, it should here. Where is it? What is this called? Example? Example.m. Where is it going to publish to? It's publishing to users, Jared Daily Documents, MATLAB. Can't tell where it's publishing to. Cancel. So the output folder is cancel. I just want to see the output name here. So MATLAB, there we go. HTML. So I don't want it to go to output HTML. I just want it to go to the output folder MATLAB. So that's what I'll call. That's what I'll do. There we go. So let's go ahead and publish that. Example. And so now it should show up as example. I'm not seeing it. Where did it go? Publish PDF entire GUI window. Use new figure. Yeah. Create thumbnail. Include code. What this is supposed to do is my understanding. Is it supposed to publish this? Oh, here we go. Let's try this. It's supposed to essentially make a PDF document that includes your code and your images, I believe. It's not doing that for me. So I don't know why. So that's still an M file, so it's not a PDF file. Entitled M. Well, I don't know what it's doing. I don't know why it's not working. To publish the results, you need to select output format. So I did that. Oh, it does not work well if you have programmed user interactions such as prompts. I don't have any of that. Script is executed, no values available for the user. Your message consists of one section. So I did what they said to do, but it's not publishing, and I don't know why. Oh, I don't know why it's not working, but it's not working. So I guess let's publish the image. Oh, there we go. Oh, I think that I had to choose what I wanted to publish up here. So let's publish the code. So it highlights the code. No, that's not what I want to do. Yeah, I don't know why it's not publishing it. I guess we'll have to publish section with title. Maybe it's over here. Insert a section. No, that's not it. Save hyperlink. Maybe I need to save this. Have I not saved this? Save. Now publish. Still no example PDF. Oh well. We'll not worry about it since we don't publish things. I don't know how to publish MATLAB code apparently. Of course, when I was doing MATLAB for research, we had to just publish it separately. We weren't able to publish it within MATLAB. We could export things, but that's all. Okay. Next, live script. So this is actually just new in MATLAB. So I've never done this either. But in live script, you can execute the code one section at a time, so each one of these things at a time, and then you can actually edit the script that's not being run. So if you're running one part and not another part, you can edit it. So that's kind of nice. So you can change it on the fly. That's really nice for really long programs. All right, next section before we die of boredom here is going to be all about importing and exporting data. There's lots of different types of files and types of things that you can import and export from and to. And on page, let's see, table 7.3. Where's table 7.3? 264, 7.3 lists all the different ways, all the different types of files that MATLAB can read and recognize. So text files, if you have a text file that's in your MATLAB workspace, it should be called a matfile.mat. So you can write a text, you can write a file as a text file and have it be .txt, and then you just change the end, change that suffix on the file to .mat, and it'll just change the file. It's the same kind of file. You also have a .dat file, which is essentially an ASCII data file, which is just a bunch of ASCII numbers, a bunch of binary numbers. And then the CSV, which is comma separated values, so it's like a text file with commas in between each number that represents the next number in the array, essentially. Then we have common data format. It can do flexible image transport, so it's like an image file, HDF, another data format, spreadsheet data from Excel, image data from the TIFF bit format, the JPEG format, or the GIF format. And then it can do audio data in 4 different forms and video data in 2 different forms. So it can recognize all those different files as just data files that it can import into MATLAB, and then you can start manipulating mathematically. So yes, you can manipulate a movie mathematically. You can do digital animation here. You can bring in a movie file and start figuring out what little pixels on the screen you want to mess with and where they are on the screen, and start messing with them, changing their color, changing what they're doing, turning on, turning off, shifting one thing to another, whatever. So you can start manipulating the screen. Excuse me. This is how the first digital animation was done. They'd create some kind of a animation using a computer, and then they'd manipulate it using mathematics. Very simple. Later on, it got more and more layered and more complex, so they could create what they call a mesh, or they often call it a wire mesh. And this wire mesh is essentially an array of numbers that defines a thing, some kind of object. And then by defining certain functions for that object, you can define certain movements for that object. So that's kind of cool stuff. Exporting. To import these things, you have different import commands. There's a UII import that's for importing ASCII files. There's I think there's just an import file as well. But you're essentially going to bring in certain files with certain names. You have to put the name in there. You have to use the right one for the right kind of file. So if you bring in the right file with the wrong function, MATLAB is going to think it's something that it isn't. So it's going to read it incorrectly. So you got to be careful with that. And then there's also writing commands so that you can export data out to files. You can read files, you can write files, import, export, all kinds of different things. Not going to go through all that. It's more trouble than it's worth at the moment. We will get some experience with it later. Then at the end here we have debugging your code. I love this. They have this picture, figure 7.11, which if you were in my engineering 1010 class, you probably recognize as the first use of debugging a computer, right? Where they actually found a moth stuck between two transistor bulbs inside of a computer and removed it, and removed the short in the computer so that it fixed it. So they actually found a bug that was debugging. That's why we call fixing our code debugging our code. But you can debug just by running your code and seeing what errors come up and fixing them. You've done that yourself. You've seen me do it. But there's also a built-in code analyzer in MATLAB. So if you go up to Preferences and go to the code analyzer, so Preferences I believe is here under MATLAB on a Mac. In Windows it's going to be under File, I believe, Preferences. But if you go there and then go to your code analyzer, where's the Preferences? Where did they go? Oh, I forgot to finish this command here. No wonder. So here's my MATLAB preferences. I go to my code analyzer. I think I know why my thing wasn't publishing now. Because I hadn't finished, I hadn't pushed pause. I hadn't exited out of the pause. So let's publish this now. See what happens. It's probably trying to publish like 10 times now, since I published it a whole bunch of times. So we'll set a wait here and publish for a little while. But anyway, we go to our code analyzer here. It will underline warnings and errors for you, or underline errors only, or you can just not underline anything. You can also do autofix highlighting color. Autofix is a fairly new feature. When I was doing this stuff at the beginning, there was no such thing as autofix. And then you can actually pick which things it's going to try to fix for you. Discouraged function usage and other things. It's going to tell you whether or not you're doing your code right, and then you can apply that. You can change it up if you want. So, useful feature that we've already made use of. So apparently it is trying to publish my thing now, but I was trying to do it while my command was still, while my thing was still running in the command window. It's still running in the command window. And it's still running in the command window. And it's still trying to do things. Okay, so it actually did publish it. Here's my published file right here. I can print it off. This is an HTML file. So this one can actually be posted to the internet. And then I'm going to hit this again. Let's see if it publishes my PDF file somewhere. Looks like it did. So my PDF it's not there. Goodness, how many times did I do that? Lots of times, apparently. Yeah, my MATLAB's kind of stuck in a rut here. That's kind of funny. I put that pause into my function up here, and now that I tried to publish it, apparently you can't publish it while your function's still running. There's my PDF file right there. So you can publish it, and you can actually include the pictures too. One of these publishes should probably include the picture. So you can publish the image and other things. You can do all kinds of things. So if I go right here, for example, at the bottom of this, and I insert the image, and then publish, and I'm here and hit enter. It's putting an error in there because I didn't tell it the name of the file name here, which is just going to be whatever it is, figure 1 or whatever. But didn't know what the image was, so I'll use figure 1. Anyway, let's move on. I'm tired of that. All right, so that is the idea behind the code debugger system, where they can help you with your code. You've seen it already, of course. And again, you'll get more experience debugging your code later. We'll use things like the timers to see if we can make code faster, or you can actually follow your code one step at a time and see kind of how it goes. There's a way to do that as well, which we'll learn about later. So that is all of our input-output stuff for MATLAB for now. And that takes us to the end of chapter 7. Chapter 8 is selection structures. We're going to move on to doing some kind of Boolean, well, not Boolean, but we'll do Boolean as well, it turns out. But next week, we're actually going to start off with a little bit of real programming. So more real programming. We've already done some functions. Now we're going to do more than that. So, does anybody have any questions before we're gone here? Before we're done? We're all good to go? All right. Well, we'll see you guys next week. Email me if you have a need. Did somebody send me something and I didn't answer them back? I'm trying to remember. I think that somebody might have done that. Did anybody send me a file and you didn't get a response from me? Apparently not? Okay. If that happens, email me again because I'm having trouble checking my email at home these days, so I'm not checking it as often at home. Mostly just doing it at work, but please send me your code if you have a question and we'll talk to you later.
Thank you.